I got a bit lost before the break. There were some packages that were not loaded, so I had to restart things. Anyway, so what we can do when we do the rescaling, so I had here, I got a scaling of a factor 10, and with that we can start getting something that looks more reasonable. Not the 3 quadrants, and 4 quadrants, sorry. But still, if you remember where the cortex is, it still isn't able to really segment that. So we need to do some other things to really find this. So what we can do, we can, for example, use it on single images. We can use it on multimodal. I write bimodal here. Can even use it on hyperspectral data. I have a material science example linked here. It's in principle looking at Bragg gauge imaging with neutrons, where we can identify different crystalline regions in the material. So that is an example that you can look at if you are interested. Another way of doing segmentation is using quad trees, and that's kind of a splitting procedure where we have the original image, which has, in this case, 2 blobs. We split it in quadrants, and we see that this one is still contains 2 high intensity variations. This one doesn't, and these 2 also include intensity variations beyond some threshold. So we need to do a second split, and this one is split again. And that one is not split anymore. And we see here, this one is also split into several regions. We can see these ones, they are now constant, so they don't need to be split anymore. And then we iteratively split until all these threshold criteria are fulfilled, or we have reached a level that we don't want to split anymore. So in this case, we say that this is the smallest box, so we don't want to split any further. And then you can see here that we have regions of different sizes, which should be more or less constant. There are different criteria. Could be statistical, so you take the average plus minus on standard deviation. You can even take the min-max difference within the region, which is cheaper to compute. So there are different approaches how you can do this splitting. And looking at a real image on that, we have this image of a grasshopper. It's not an alien. You can see here when I run it, I get a lot of jitter along the edges because there is no real good information. But otherwise, you can see that out in the air, you have some larger regions, and when you come closer to the contours of this grasshopper, you have very tiny boxes. And that is a way that can be used to focus on different regions better. Afterwards, you can also do maybe some region merging. So you say that all regions which have the same average value, they should be merged into one class. But that's the post-processing step of this quad tree splitting. Can of course also be done in 3D, but then instead you have cubes that you split into subcubes, so then it's octree. And the whole thing can also be constructed as a tree structure if you are into data structures, and you can do some quick searching within these. The further development on that is to work with superpixels, and that's a bit smarter thing, and there are more information about those. You can see here that it's more like kind of mosaic style, and afterwards you can decide how large these pixels should be, depending on what level of detail you need to look at. You can see this the upper corner is fine-grained, and the lower part is really coarse and more get into the features, the larger regions. Why we can use it? With that, we can actually drastically reduce the size of our images. If we just have this representation, you saw that we had much more smaller regions, and can also serve as some initial segmentation, because you already have some, say, spatially meaningful groups that you can work on. And here is an example of some rock, clay, and pore space image. And if you look at this image and try to do some multi-class segmentation, you get this. There is a lot of different small subclasses. It's very fractured. It's not so easy to really tell. And you can even say that these, what is it? Magenta? Doesn't look magenta right now, but anyway, I think it's magenta. These regions, you can't really see them in the real image, so they don't really make sense. So what we can do is we can try to generate these superpixels, and then here they are just colored as they come. And if we look at the contours of these superpixels, you can see that they actually are framing in larger regions, and that can give you some help to better analyze this image. Still, you have around here, you can see this skin effect that I showed you previously. So it's not the perfect way, at least not the way it's tuned here. You can probably tune the parameters a bit more and get better results. And then we can also do merging, as I said, with a quad tree, that we merge some regions which have more or less the same average value. So then we can get these segmentations of the regions. But yeah, you see again in this area here, it's a bit ambiguous exactly what class we have. Is it a real feature or is it something else? And then we can continue also doing more segmentation on it. So here you can compare what the pixel segmentation looked like, and this is what the superpixel segmentation looked like. Yes, I'm actually a bit confused that that one and that one turned into the same class. That doesn't make sense to me. I have to look into that actually. Yes, so now we have concluded the first part. We looked at some histogram-based thresholding. We looked at clustering using k-means and some region-based segmentations with quad trees and superpixels. So all these are unsupervised, meaning you just kick them off, maybe with a starting parameter, and then they do something. And the next step is going into the supervised segmentation, and there it is. Oh, I'm on the wrong spot. Sorry. So now I'm in the right spot. So we have some different methods that I'm going to show you. Then for the workflow, I'm going to introduce a concept called pipelines. And then with those, we look at different types of classification, regression, and segmentation. And there is some reading material. And in this lecture, we have a lot of new packages to look at. There will be more later. But again, we look a lot at the scikit-learn package. There are a lot of tools there that we need. And let's go on. So with the supervised learning, you usually have at least two steps. You have a training phase and you have a prediction phase. In the training phase, you always have to have a set or most cases, have to have a set of input images and what you expect to be the result. And that is how the training is going on. There is also unsupervised training where the networks or the algorithm is feeding back and coming to some conclusion. But in principle, we need a training phase. And after that, we have our model that is trained for a specific task, and with that we can do prediction, and then you only provide an input image, and the prediction should tell the classes or the category of that particular image. And that is when you use the new and unseen data. And there are a couple of different supervised methods that we can work with. We have the classification, we have regression, or combinations of the two. So let's first look at the classification. We go back again to this blob data, where in this case I have 3 classes as the training set. And if you look at these, you have the coordinates and you have different group IDs. So you have zeros, ones, and twos in this class, in this blob cloud. And now we want to find a way how we can tell what a new point where it should belong. And a classic algorithm for that is the k-nearest neighbors. And it's quite simple principle. So look at these hikers. They go in the forest and they want to tell which kind of forest it is. And the green one, he says it's a pine forest, no doubt. But it depends. He can do this conclusion on how many trees he sees. So let's say he can only see 1 tree, and from that he wants to tell what kind of forest it is. So he certainly tells it's a pine forest. This one, well, depends exactly where he stands, but let's say he sees the pine tree, so he also says it's a pine forest. This one says it's a birch forest. And well, that would be okay if they only see 1 tree. If they now see, let's say, 3 trees, this one, he still sees 3 pine trees, so that is okay, so it's a pine forest. This one now, he sees 2 birches and 1 pine tree, so now he says it's a birch forest, even though it's mixed, but he can only give it 1 category. And the last one, well, he sees only birches, so that is what he says it is. And depending on how many trees they look at, you can get more or less robust results. But you can also bury some outliers. So you have to tune the training depending on what kind of outcome you want. So let's look at this assignment. We have our blobs. We have point A, which is just between the yellow and the other 2. Which one he would choose depends, again, how many neighbors he would work with. So if he would look at only 1 neighbor, I think in this case he would say it's green. If, however, he would look at 2 neighbors or even 3 neighbors, then he would more tend into saying, it's more like the yellow. This dot C is certainly, no doubt, it's the green class. And again, this orange point is a point of confusion. If he only sees 1 point, he says it's green. And if he sees more than 1 point, say 2, 3, then he gets more certain that he belongs to this class. So with the number of neighbors, you can tune how sensitive he is to uncertainties in the overlapping region. We can also do a little text example. In this case, I train with this table. I have the values 1, 2, 3, 4, and I say that the classes I have assigned is I am a dog, and each one gets a number. And if we try to run this example, we look at the test first. We just do k-class predict, and we look at 1, 2, 3, and out comes naturally this I am a dog, because that's exact match to the points. However, if we start looking at points between, so now I look at point 1.2, that turns into am, because 1.2 is closer to am than to a. And same, it's rounding down actually, so it's actually 1.5 also turns into am, while if you start putting in 1.8, then it says a. However, if you now go beyond, far beyond what you have trained, so looking here, in this case, we put an input 100, then it says a dog, because dog is still the closest neighbor, even though it's far, far away. So as long as you're in between, you can do some good prediction. If you're far away, it can be questionable if it actually makes sense to make a prediction with that value. So let's go back to the blob data. Now the blobs are a little bit more mixed. So you can see here there are some greens and some magentas in here. And let's see how that one segments. So we train a model again. We have k nearest neighbors with one neighbor, and we try to do a fitting and see what happens. So if we try to put it in this training data and do our test points, the test points are in principle just, in this case, x and y coordinates between -5 and, between the min and max in these data sets. So we just do a grid and test every point in the grid with this predictor. And the output is we get a somewhat convincing line between the yellow and the other two. This little outlier here comes from that dot. So as we use the nearest neighbor, this dot is the closest, and that actually gives this bulge in the line. However, if you look at the intersection between the other two classes, you see here, not with today's light, so maybe I should shade a bit. Is that one? No. Oh, that's the wrong one. That one. Yeah, hope you see it a little bit better, but it's not very visible now today. But anyway, you can see in this region, you have really a chaos. There are some greens mixed in between, and that is because you only have one neighbor. So let's try another case with increasing the number of neighbors. So in this case, we train a 4-neighbor predictor. And let's see, we do the same training and put the same training data. And now you can see that we get a much nicer line between the yellow and the other two. And this little outlier here didn't have the power to change the decision line. Also, in the region between the other two classes, you see that that's a much clearer line between them. So by increasing the number of neighbors, you can get much more robust segmentation between these classes. Then we can also do linear regression. Typically, you have some kind of system matrix that describes how data measured points are related to input values. And the purpose is you want to fit some model, theta, and see what comes out. And the classic is just linear regression. Here I just put up some numbers. So we have a slope of 10, an intercept of 10, and then we get these points. So that's a very trivial example. But we can do it even with two-dimensional data, or we'll first do some testing with this one. So we have done the fitting, and we do prediction, and we put in different values and see what comes out. And here you see you get this equation computed, so it looks that it makes sense with this fitting case. So if we do it on the blob data, we have our two classes. We have zeros and ones in the two classes, and then we have some coordinates. And if we compute the regression of that, we can also compute some kind of slope and offset, and here you get those values for that. So here you get actually two slopes, one in x and one in y, and you have the offset. And plotting that with the test points, same as we did before, you can see that there is a gradient going from the lower left corner to the upper right corner. And it can also be visualized as a test image. You can see the gradient a little bit more clear. Now we can say that we put a threshold on this regression plane. And when we put that threshold, you can see that you have a nice segmentation within this fitted plane. In particular, if you put in the dots, you see that it actually makes pretty much sense. Yet another way to do this classification is to use decision trees. And did any one of you study computer science or something relevant? Yeah. Then you know trees in that case. Yeah. Trees are usually in nature. They have they have a stem, they have branches, they have leaves, everything going up. In computer science, you draw your trees upside down. So you have the root is in the top and you have the leaves in the bottom. It's a convention. So that is the way how they are represented. And in this case, it's usually about making decisions. So you have a point here and you decide, given some criterion, you go left or you go right. And that will help us in our segmentation task. So here we have a decision tree to classify if a number is odd or even. And we do the training. We have our data, 0, 1, 2, 3, and we have 0, 1, 0, 1 to tell if it's odd or even. And if we fit this tree, we can see that we have a tree that comes out like this, and here you have the decision criteria. If you are below a half, then you go left, and then you land in this leaf, and you say it's odd. You can see the value here. You have only one value inside. One is said to be even, and one, no, wait. The 0 comes here, sorry. And then you have one even and no odds. The other one brings it down here, so you have still one even and you have 2 odds. And then it sets again a threshold. If it's below 1.5, then it goes in here. And you tell that that one is an odd. And then you see in the end, all the leaves here, they tell which class it belongs to. For this, you also have kind of an unbalanced metric, which is called the Gini index, which is the sum of all contributions in this, how many representations you have in each. And Gini 0 means that it's very homogeneous, and Gini 1, which is the greatest number, is that there is it's completely arbitrary. And you can see here how it changes. You have in this, you have Gini 0. In this one, you have 0.44. Then you go into a leaf. You see that the leaves always have a Gini 0.0. And that gives you an indication on how to split these trees. So let's try a decision tree on the blob data. Same data as we had before. And here we had apparently 34 in category A and 33 in B and C. And in the end, in the leaves, you can see that all 34 are grouped here, and here you can see that they are split up in each class. Let's see what that turns into. Something like this. And, well, kind of makes sense. Maybe not the best separation that I would select, but it's actually a solution. So let's try something else. We can also do random forests. So if you have one tree, it's a tree. If you have many trees, it's a forest. So what is happening here is we actually do many trees, train them on different sub-data sets, and see what happens. And then we do it the Swiss way. The majority wins. So you ask these trees, which is the strongest choice? And that is what assigns the class. So for making a useful example for that, we do the blobs a bit more mixed up. So you can see that there is a lot more overlap between the classes. And here we want to find some kind of tree that can solve that problem. So let's try in the forest. We have, in this case, we have 5 trees. And we start doing the training. And just to look at what one tree looks like in this case, you get that tree. And the other trees, they look more or less the same. So these trees, thanks to the great overlap between the classes, get much more complicated than in our previous case. And looking at the training data again and testing how the performance is, here you can see the outcome of the forest classifier. It does a quite decent solution. There is some overlap, but we can't do much more about it because it's so heavily overlapping. And then we can look at the outcome of different trees. And you see here that this one made something quite crazy, and probably the other 4 trees didn't agree on that. So that part is actually rejected, and that is why we get the final solution like this. And you can, of course, train it with more and more trees, but at some point I think you will get overtrained and do a very specific solution on just that. Pipelines is something, it's actually a tool that we can use. It's more like a programming tool that we can use for doing more efficient testing and also easier to work with programs. And in principle, what it does, what it contains is a sequence of transformations and predictors, and you can put them in a cascade behind each other without any branching. So it's just doing one after the other in a long chain. And let's try it on the blobs again. So here we try to create a pipeline where we have the first step is just that we create a pipeline which has the task to normalize, and there is in the scikit-learn preprocessing we have something called a robust scaler which normalizes the data within the range plus minus 1. No, it's statistical. So it's probably the standard deviation minus average divided by standard deviation. And then we get this distribution. So from the beginning we had plus minus 10, and now it's shrunk together because many of these algorithms, they work best if they have normalized data. In particular, if you have multiple feature vectors, then it's of real importance that you can normalize it. Otherwise, one will be very dominant in the training. So we can also do even more. We can do some kind of quantile transformer, saying we want 2 quantiles and add the scalar again. And you can see here the way it's programmed now is that you create a pipeline, and in the pipeline you have a list where you have a label and an algorithm that you want to work with. And then you just add on more to this list. And in the end, when you have the pipe, you can just do the fitting and put in the values and things will happen. So here you have the input data, and first it's the wide span. You can see that it's actually a little bit distributed on different places. In one you only have 3 categories. In the other ones it's more tending towards the negative values. This one has 2 modes. And after the normalization, everything is squeezed in, or the quantile, everything is squeezed in between 0 and 1. And then we do the normalize, and it's again a little bit modified in how it's distributed. So then we can add polynomial features. We saw before that we sometimes can have an advantage in adding polynomial features to our regression models, or also the segmentation models. So here it's a possibility to add some polynomial features, so we compute a higher order polynomials of the value. And the messy pipe, which is called here, we can do a fitting again, and now you can see that we added a lot of feature vectors into the data, and you can see here how it's distributed in the histogram. Now we just look at how the pipeline is built up, what kind of transformers we can use, but in the end we also want it to do some kind of classification. And what we will work with is, in principle, now first the MNIST database, where we have the numbers, digits 0 to 9. And we want to classify and say that this is 1, this is 9, etc. So let's build up some kind. First we need to load the data. We take from MNIST, we take the first 50 images. And we see here that the image data is 50 images with a size 8 by 8. Then we load them, we flatten it a bit, we normalize, and then you get the first level for the preparation of the data done. Then we want to do a k-nearest neighbor classifier with 1 neighbor. And we run the fit, and you can see afterwards what the output is. It doesn't really make much sense how you see it here. But let's test the performance. And when we run this prediction on this data, we have 100% accuracy. Looks fantastic, right? We look at the confusion matrix. Everything is really nice. There's no misclassified pixels. And also we can look at the classification report and get some precision and recall, F1 support. Looks fantastic, right? Let's patent it and sell it to Google. No, it's not really that good. So let's bring it to a harder test. Let's create some kind of number here, or image of something that should be a number. And we say the real value of this one should be a 9. Kind of looks like a 9 or something. But the prediction is 7. So it's not so good anyway, this algorithm. So what has happened? I actually browsed rather quickly through it, but when I did my testing, I actually took the exact same data set for the training as for the testing. And if you have k-nearest neighbor and you use that, you have a perfect match. That means I did something wrong and you should definitely not do this, that you train and validate with the same data. So what typically is done is that you have your data set, you split into 3 parts. One is for training, one is for validation, and the last is for testing. Sometimes you don't need the validation, then you just do the training, but for deep learning algorithms, you need a validation, so you train on one part. Then to get the feedback for the feedback loop, you need the validation data. And finally, when you test the performance, you need the test data. So you have to split your data in these categories. How you split it depends a little bit on the application. There are different ideas. So sometimes it's like 70 on training, 20 on validation, and 10 on test. But there are different distributions in that. But it's important to really be aware that you can't validate and test using the same data as you used for the training. So I went to jail. So let's go on. Now we try to do regression with the pipeline and see what we can do with that. And now, instead of putting it into a category, we want to have some kind of regression that if you put pixels in this configuration, it will predict the decimal number that we had. And we go and get the images again. And in this case, we train with 50 images, and we validate with quite a lot, actually, with 450 images. And then we can run it through the pipeline. So we again do the flattening, normalization, and then we do k-nearest neighbor regressor. And then we do the fitting, and then we can see what comes out. And it's probably easiest to see in this one. We can see here how the predictions from the training data set is that the predictions, they are pretty good. We're actually pretty well focused around. But if we start doing predictions with the validation data, you see that, well, mostly it does a good job, but there are cases when it actually predicts the label very wrong. So this is a way of showing, this is not the confusion matrix, but it shows still how the values can be estimated. And then we can look on with the increasing neighbor count and see how the performance improves. And looks still a bit strange. But so probably we had too many neighbors in that case. Then we can do segmentation, doing single values or single class in the segmentation. And this is where we go to a quite messy image. We have this mitochondria from a microscope image. We have not the best signal-to-noise ratio. We also have a lot of structures that we don't want to segment. And trying to put a threshold on this is useless, because you would get a lot of misclassified pixels everywhere, and not only the mitochondria that we want to see. And now we are going through quite a lot of different methods to do it. We can do it try with decision trees, random forests, linear regression, nearest neighbor. And then finally, I'm going to show a very simple little deep learning UNet, how that is built up for this task. So let's try. We have our data, which is, this is the input, and this is what it should be. This data set is available in the EPFL, Computer Vision Group database. So it's, I think it was 160 of those slices as training and test data. So there is quite a lot of data in that data set. Let's continue. So let's just cut out some smaller pieces because we don't want to wait too long here for the processing. So we have here now the training mask looking like this, training image like this, and then we have the validation image and mask on the side. Then we try to do a regression tree and see what that can do for us. And in principle, we try it, we train it, and the prediction from the mask turned out to something that wasn't really convincing. So the tree as such may not have been the best choice. Looking at the full image, then we look at, so that would be the training mask is about here, and the validation would be here. And you can see that the prediction does the same messy thing on both the trained and on the validation part. So let's try with some k-means and random forest. Then we add even some extra components of positions and try to normalize it and getting the k-means out of it. And the result from the prediction, from the training data, is actually pretty good. It extracts these mitochondria pretty well. However, if we look at the validation part, you can see that in the part that we were well trained, it works well, but after that, it doesn't have a clue. It just gives something rubbish. So again, that was a tricky one. And now we just build on and play with different things in this pipeline, and there are some more examples. Time is running away, so I'm not going to look so much into details here. We can add also some filtering features, which in the end actually starts bringing something that looks like what we want to have. So there is a possibility. That was an empty slide. So we can easily modify these pipelines and try and test things. You can even save them and use them for other purposes later. But in this case, what these choices we did in this test chain, they were not really so successful. So maybe we should look into something else. And then we go into the neural networks. And the principle of that was developed during the 90s. And at that time, it was just for single values, where you had some inputs in some network here. So you have some values coming in. And these inputs, they are sent over to the next level of nodes, which as a weighted sum. And then the output is done with some activation function, usually a sigmoid or a ReLU activation function. At that time, it was only sigmoids. And then finally, you get some output, which is a probability that it belongs to one class or the other. So that is the basic neural network. And this is, again, a supervised method. So in the beginning, you need to have some training input data and some ground truth that you compare to each other. And that is then backpropagated with the help of optimization algorithm that optimizes all these weights in the network in order to bring a realistic result. The development went on, and during the last 20 years, we got new graphic cards, and we could do much more fancy stuff. So that brought us the convolutional networks, which were much larger, they were deeper, they had more nodes, they had more layers. And the important thing is the convolutional, because each of these nodes now actually perform a convolution of some kind, and each node contains also a kernel of a specific that is sensitive to specific information. So now the training turns into tuning not only the weights, but also the shape of these convolutional kernels. And then you put them in cascades, and Then we come to the so-called UNet, which today is used a lot for segmentation tasks, where you have some input layer, and then you have different kernel sizes. You do some downsampling to look at different scales, and you do even more downsampling, so that's where you get this downsampling side. And then you can do the upsampling, and then you get the U shape of this network. So that's why they called the UNet. What is also given is that the output is not only downsampled, but it's also forwarded to across to the other side of the network. So that was a UNet in very short time. If you want to learn more about it, I recommend you to go to the literature, maybe even do a machine learning course where you learn it in detail. I just want to give you a little bit glimpse into what these look like, what they are about. And the important thing is that also they are not so difficult to implement. There are packages. In this case, I'm using TensorFlow combined with Keras. And there is also PyTorch, which is another Python package for you doing deep learning. And here you have some basic components. You have input layers, you have convolution layers, you have downsamplers. And you can see here I have a couple of convolution layers, downsampling, convolution, downsampling, and so on. And then I have this concatenate that brings this bridge over that I showed. And this list of different components are then put together into the model, and that is our network that we're going to work with. And if I just press here, it should be okay. I get a lot of warning messages, but that's just telling about my GPU. And it's important, actually, when you work with these networks, that you activate the GPU-based model, because otherwise you will wait a long time. So let's look at what the network we got, what it looks like. We have now, first in table form, we see we have an input layer which has no parameters. Then we do the first convolution. We already get 640 parameters to tune. And you see here that we have quite many parameters that need to be tuned by this optimizer, and that is actually what takes a lot of time when you try to run the training over many images, that all these parameters need to be fixed and tuned. We can also take a look at a schematic view. Looks like this. So now you can see it more in graphic way. Where you have the convolution layers, you have the pooling, does the downsampling, and then you have the U upside down. I don't know why they have done it this way. I tried to flip it, but they don't want to. Sometimes you can also get it vertically. That's also a way to display it. So let's try some training data. Now I loaded some of these cell images, and we got some data. Looks like this. Actually, we don't see everything on the screen right now. So actually, I think I should switch to notebook view and continue from there. And then we see now that we have these different images. We have the training image, we have the training mask, which comes from the full image. That's already a little bit not recommended that you take the training and validation data from the exact same image, but right now I'm minimizing the overload. And then we look at those. Now let's look at the untrained model, what it does. And if we didn't train the model, it just gives us some rubbish. It doesn't really make sense. And of course, it's not trained, so it doesn't know anything. And then when we continue, we can try to make some training. And for that, we need some metrics. So we have to measure the output versus the input in order to tell the trainer that you're doing good, you're doing bad. And for that, we have binary accuracy. We also have the mean absolute error. There are also another one would be the dice score, which is a combination of true positives and true and false positives, etc. And with that, we can now start training the model. We set an optimizer, which is the algorithm that actually tunes the weights in the network, and we compile it, and then we ran a couple of iterations of the training, and during the iterations you can see how the different loss functions, how they behave. It's just a lot of numbers right now. Now I did 20 epochs, and with this small data set, yes?
Isn't epoch like different parameter tunings? Like each epoch is like...
It is in principle an iteration of the training. Okay. So it does the parameter tuning and sees, okay, I get this output, so yeah, it is a parameter tuning. So it's an optimization part of the iteration.
There's only 20 changes to the parameters throughout the...
No, it does, tries to optimize everything.
So you have 1,000 parameters, but it's not like 20 different versions of those 1,000 parameters being changed. That's how to explain it, but I'm just trying to understand what each epoch is.
Each epoch is trying to do the best optimization given what it already has. So given the weights it has and what the optimizer can give back. Okay. What it does under the hood is quite a lot. Actually, I can't honestly tell exactly what it's doing, but it's the best optimization you can get from the network it has and the data it has, and then it tries to optimize that, and then next epoch takes the same training data, but with the new weights, and tries to do the best out of that. So that's the task of the optimizer, and then by iterating that many times, you get closer and closer to something that you can trust. So, and then you can see, oops, that one I need to fix. So, then you can see here the error is going from 50%, that would be flipping a coin, more or less, and down to something like, no, it's not percentage, it's just some value. But anyway, it goes down pretty steeply, and then at some point it levels out to something asymptotic. The classification accuracy on the training data is quite good, but not going towards the 99%, which we would have wished. And the validation data also levels out a little bit less. Now you have to keep in mind that the data we have is just a single image. So we don't train on a lot of data, and these are data-hungry methods. So you really would like to have 1,000 images of that kind in order to train well. But then we are not in the scope of what I can do during this lecture. And not on my laptop. So, and let's try what it does now. I get some warnings. And now we can see that the predicted training is doing something. It's getting a little bit better. And you can start seeing these objects, but still it's not as good as we would like to. But I think for getting better results, we need more data, more training. And actually, if I would start the training again, it would get better and better, because it's working on the existing model and trying to refine that one. So if I would do a new training here, that would be, in principle, training step 21 and forward. And then there should be some improvement, I believe. And at some point, it's overtrained, and then it starts doing too much, actually. So then here is something strange going on. Yeah, now I think I'm a bit saturating my laptop. Yeah, then everything starts turning into the same class, so maybe not the best. So, and then we can try something else. And looking at the loss history of that, it's doing something. Let's see. Yeah, and now after that modification we did here, I think I changed some of the parameters, what kind of loss function I used, and that made the difference here now. And with that, we now start getting the mitochondria and less of the other things. What you get here is a probability map, so it's not really black or white, but it's the likelihood that it is belonging to the class you ask for. And then afterwards you have to do a thresholding, which is easily done with Otsu or something. Yes. So let's switch back to the last part. I'm running quite over time, but so some comments. This was a quite small model. I also trained it with limited and far from ideal data, but we could see the main building blocks that are included. And if you want to specialize into this field, there is a lot more reading to do. I don't have the time during these lectures to tell you all that, the tricks of that trade. But anyway, you have hopefully got an idea how these networks are built up and what you could expect from them in the future. Another model, which is a different kind, which you probably have seen in some cases, is the SAM model, which stands for Segment Anything model. And this one is a model which is quite big already. It's trained with a great variety of images, and it's not the same way as the UNet, but it's more a transformer type. So originally it was done on the same type of models as the text interpretation, natural language interpretation. And now it also requires some cues. So when you do text interpretation, you write some text, which is interpreted and put into an answer. Here you need instead some markup points. This was done by hand. So I just selected some point to identify this tumor. And what it did afterwards was actually to segment the contour of the breast, and you have the tumor here with a slight misclassification. So this was an example. I got it running in 2 hours, including installing, downloading all the needed model data, etc., and got this example. So getting started with this model is quite fast, but afterwards you probably need to tune it and prepare it for your special purpose. What you need to know is that you need to have these markup dots, so it's not so well suitable for automatic segmentation. But it can be very useful, for example, so I see the best use is to create the masks for other types of training. If you look at the differences between the UNet and the SAM, the UNet is a fully convolutional network with encoder-decoder architecture, and it must always be trained in order to be useful, and it's trained then for a specific task, and also actually the whole architecture is built up to meet the needs for a specific task. And for that task, it can achieve very high accuracy. SAM, on the other hand, is large pre-trained network, quick to set in, and it can actually segment everything in a single shot manner. So you just plug in an image and then it works. But what you need is user-guided prompts in order to make it work. And that brings me to the end. So today we looked at, in the beginning, with histogram-based segmentation methods, and now in the second part, supervised methods and how we can include those into pipelines. And in the end, a very quick snapshot into the world of deep learning. And well, with that, thank you for today.